first thing we're going to do is we're going to go back and relive some glory days of pre-calculus algebra. A line contains 2 points, 1, 5, 7, 17. Determine the equation of the line in the y equals mx plus b form. Yay! What we have to remember is, let's see here, our slope is delta y over delta x, and we can determine the equation of a line by m x minus x1 is equal to y minus y1. Go ahead and determine the slope, determine the equation in the y equals mx plus b form. Check your answer for somebody around you. Liam, what's our slope come down to?
2.
Slope comes down to a value of 2. So we can pick either the point, does not matter. And solve this and put this into y equals mx plus b form. Katie, what do you come up with? Get an equation yet? Drew, what do you come up with?
2x plus 3 minus 2x plus 3.
Y equals what? 2x plus 3. Where we have 2x, and then we have a minus 2 is equals y minus 5. Add your 5 over to both sides. So y equals 2x plus 3. This would be our equation of the line. Okay, once again, we are just reliving the glory days, pre-calculus, beginning of calculus, just determining the equation of a line. Well, we have equations here that we're going to be dealing with. We have our base equations that we have here with the velocity, acceleration, and time. Okay, we have delta S over delta T, delta V over delta T for acceleration. We can relate that to the idea of what we have here with our slope also. A car travels at a constant velocity of 10 meters per second. Write an equation that would relate the displacement in meters of the car to the time in seconds. Graph the relationship. So we have displacement and we have time. Okay, we're trying to create a relationship, the relationship between displacement in meters and the time in seconds. So my chart, I'm going to have T here, then I'm going to have D here. after 1 second, how far has the car traveled after 1 second? Ozzy? 10 meters. Because we have a velocity of 10 meters per second, this is going to give us 10 meters. After 2 seconds, how far has the car traveled after 2 seconds, Brandon? 20 meters. After 3 seconds, how far has the car traveled, Riley? 30 meters. So if we take a look at a graph, and I'm only going to graph quadrant number 1. I get little tails here in quadrant number 1. My horizontal axis is going to be time in seconds, and my displacement is going to be in meters. If we plot these points, after 1 second we have a displacement of 10 meters. After 2 seconds we have a displacement of 20 meters. After 30 seconds we have, or 3 seconds we have a displacement of 30 meters. And what is created is we've created a graph. Okay, and this graph should look like a line. Hopefully, looks like a line. That would continue onwards from time equals 0. And what we also ask here is determine a relationship. Determine an equation that relates the displacement and the time. Well, I have ordered pairs here of 1, 10, 2, 20, 3, 30. We can find the slope of this line as, well, slope is defined just as delta y over delta x. But in this situation, my y-axis is turned into meters, or displacement. So we have delta D over delta T. And if you want to, you could also use S up there. And this would be delta S then. So if we find the slope of this by the exact same way we did before, changing y over changing x, or delta S over delta T, or delta D over delta T. using our ordered pairs that we came up with. Dylan, what is our slope? 10 over 1. We go 20 minus 10 over 2 minus 1. We get 10 over 1, or 10. And if we take a look, this is meters and this is time, which is seconds. So we have meters per second. If we take a look at an equation, we can use either one of our points here. Either one of our points, where we have x minus x1 is equal to y minus y1, but now we have d's and t's in there. So we have 10 d minus x1, it does not matter which point we use, x minus 1 is equal to y minus 10, which is, once again, d or s minus 10. Oh, should be a t there. There we go, my bad. So we have delta x over delta x and delta y, t minus 1. And I could use either of the points. If I wanted to use 2, 20, 3, 30, that would be fine also. Distributing, we have 10t minus 10 is equal to d minus 10. So we're left with the 10s cancel, so we're left with d is equal to 10t. Well, the thing to pull out of this a little bit is that we got a relationship between d and t, but also taking a look at the slope here. This slope is 10 meters per second, which is also what in regards to our problem here? What is that 10 meters per second within the problem, Liam? Yes, it's the slope, but what else was it? The initial velocity. So our velocity was 10 meters per second, which is the exact same thing as our slope. So when we talk about the slope of a displacement time graph, this is equal to a constant, or equal to a velocity. This is equal to your velocity. So when dealing with the velocity time graph, or I'm sorry, displacement time graph, when you calculate the slope of a line, that's going to give you a velocity. Which takes us to the next side. We still have our base equations up here, but what we have here is we have a displacement time graph. A displacement time graph. This tells us how much, or what is our change in position when, once again, when we have displacement. Displacement is defined to us as the change in position. I'm here, then I move 10 meters over there. If I move 10 meters over and come back, my displacement is 0. So you can have a 0 displacement and over a period of time. if we take a look at 3 seconds, what is our displacement after 3 seconds? Well, our displacement, once again, is our vertical axis. So what we can do is look along that horizontal axis, find 3 seconds, and figure out what our displacement is at 3 seconds. Ashton, what's our displacement after 3 seconds? 4 meters. Because this right here tells us our dimensions, so it's 4 meters. What's our displacement after 5 seconds, or at 5 seconds? Okay, this is not difficult here, we're just reading a graph here. Displacement in 5 seconds would be what? Tess? 9 meters. So I go up, I'm at 9 meters. What is the displacement after 8 seconds? When t equals 8? Jordan? -3 meters. Okay, make sure you get the meters. Basically, what you're taking a look at, this is displacement. I'm traveling 2 meters away. Then I travel another 5 meters away. And then I start coming back. So what we're doing here is we're traveling a short distance, then another short distance, and then I'm turning around and I'm walking all the way back to here. Okay, so for my position where I initially started, if that direction was positive, I'm now in the negative direction away from it. What is the displacement after 10 seconds? Or at 10 seconds? Katie? 2? Looks like 2, right? Yeah. 2 meters. So once again, the motion, here's our motion here. I'm starting here. I'm saying that's my positive direction. I go, I come back, all the way here, and then I travel back to a spot that's here. Okay, so I'm just walking back, pacing back and forth here. What's the velocity from 0 to 2 seconds? So now I'm talking about from 0 seconds here to 2 seconds here. What is my velocity from here to here? Well, what we just worked on the other side, what we have is we have a displacement time graph. We have a displacement time graph. And if I want to calculate a velocity, how do I calculate a velocity on a displacement time graph? Drew? What did we do on the other side? What was our velocity? Okay, delta D over delta T, or delta S over delta T, which is the what of our graph here? The slope. So we are looking at the velocity, which we defined on the front side here, is the slope of a ST graph. That's what we developed on the front side. When I talk about the slope of a displacement time graph, I will get my velocity. So what I have here is I have 2 ordered pairs, 0, 0, and 2, 4. So I need to find the slope of this line. Well, how do I find slope? Delta S over delta T, or delta D over delta T? So I'm looking at delta S over delta T, or delta D over delta T. So I find the slope of that segment. Ozzy, what's the slope of that segment? 2 what? Meters per second. We can go 4 minus 0 and then 2 minus 0. And meters are on top, times seconds on the bottom. What's the velocity at 3 seconds? What's our velocity at 3 seconds? Well, Nate, what type of line do we have at 3 seconds? Horizontal. What's the slope of a horizontal line? 0. 0. This is a horizontal line. And if we have a horizontal line, the slope is 0, which means our velocity is going to be what then? 0 meters per second. So once again, as we're looking at the motion now, let's take a look at this motion. I'm walking out 2 meters and then I'm pausing because I'm not moving. Then I'm going to walk a few more meters out. Okay, so that's the motion that's happening there. I'm walking out, I'm pausing, and then I'm walking again. What's the velocity at 7 seconds? Well, if I go up to 7 seconds, here I'm on that line, but that one's sort of tough because do I have a value 2? Is it 2 there? I'm not quite sure. But what we have is this time spot here, 7 seconds, is a part of this initial or this long segment here, which I can find ordered pairs along this segment. At a value, time equals 6, my velocity here is going, or my displacement here is going to be 9 meters. And this point down here, what would be the ordered pair of this bottom point here? Ozzy? 8 and -3. So this point right here is a part of this line. And what we said as a part of this line is going to be a constant velocity. Okay, so this is going to be a constant velocity. And how I can find my constant velocity is delta S over delta T, which is once again our slope. So now I have my 2 ordered pairs here. Go ahead and find your slope. Lucas, what do you come up with? -6. -6 what? Meters per second. So if we take a look here, we have our slope, we have delta S, which is 9, doesn't matter which way we go 9 minus 3, or 9 minus a -3, subtracting our 2 y values over 6 minus 8. And if I do the other way, if I go -3 minus 9, that is fine. This gives me 12 over -2, or -6 meters per second. And if I go the other direction with this, we can go -3 minus 9 over 8 minus 6. We get -12 over 2, which still gives me my -6 meters per second. All we're doing is we're taking 2 ordered pairs and finding the slope. Okay, there's nothing different than what we did in algebra. And once again, since we have a line here, it does not matter. That's going to be -6 meters per second all the way along here. So if I take a look at motion, okay, I'm walking out at one pace, I'm pausing, I'm walking out maybe a little faster, pausing, but then I'm moving really fast over here because I have a negative 6 meters per second. The slope is steeper. What's the velocity at 9.5 seconds? Right here, what's my velocity? Two ordered pairs we should have is 9, negative 3, and 10, 2. Dylan, what do you get for your velocity?
5 meters per second.
5 meters per second. Once again, we can go change delta y with delta x. So we have 2 minus a negative 3 over 10 minus 9. Or, I'm sorry, 9 minus 10. Sorry, 10 minus 9. Yeah, very good. So we have 5 over 1, or 5 meters per second with our velocity. Dealing with graphs, we need to be able to read our graphs and see what happens with respect to our graphs when we have displacement time graphs. We're going to talk about velocity time graphs also. That's what we'll talk about tomorrow. We'll go through different types of graphs and working with the different types of graphs and being able to calculate certain things. And what we are going back to is we're going back to base definitions of slope, but we're also going back to base definitions of what we have done here in physics. Okay, our velocity, change in displacement over change in time. We're using the exact same thing, but putting that into an algebraic mode now. Questions you have? QED, as done. We'll work with more notes tomorrow.